Hello, my name is Mr. Wilke, and we're here to review the entire stat class in 91 minutes or less. I've got some people over on a Zoom call. Hello, people on Zoom. So if there's an audience, it's those guys, although I think they're all muted. Anyway, let's start talking about the first thing we learned, which was individuals. Does everybody remember what individuals are? Individuals are the objects described by the data set. The characteristics of those individuals are called the variables. All right? Variables, we had two types, categorical and quantitative. So, categorical variables are, we place the individuals into one or several groups or categories, hence the name categorical. Quantitative is there's numerical values for adding and averaging. All right, so we would put these data sets into what's called a distribution. The distribution is what values a variable takes and how often it takes them. Clearly, I thought this was important enough to write down the definition where everything else I just said it. Most of you guys, if you're taking the class, should already have all the notes down. You don't really necessarily need to take notes, but you can if you want. But sometimes I'm going to write something down because, well, this is stuff you need to know. All right, so distribution, what values a variable takes, how often it takes them. So let's talk about some visual ways to show these distributions. We have things like bar graph or a histogram. Got people coming in, so if I walk out of view, it's because I went over to the Zoom and let some people in. Welcome, we've already started. Bar graph, histogram, do we know the difference? Let's hope. Bar graphs are generally for categorical variables, histograms are generally for quantitative variables. Histograms, the bar should be touching. Bar graphs, they should not. All right, we had pie graphs, named because they look like pies. Okay. Dot plots. Dot plots look suspiciously like histograms, except instead of bars, they have dots. Stem plots, also suspiciously like histograms. Okay, but a stem plot, you write down the stems, the leaves, and so on, but it works out to where it's going to end up looking like a histogram. Also, make sure you have a key. Okay, describing a histogram. Anybody know the three things you need when you describe a histogram? Three things you need when you describe a histogram are the shape, center, spread. All right, shape. Let's talk about that first. Shape. What are some shapes we can use? There's this one, which is uniform, symmetric, single-peaked, symmetric bimodal. This is a much better roller coaster. We have skewed which direction? To the right, good, and this one is skewed to the left. Okay, so the shape determines what we're going to use for center and spread. So if it's symmetric, like this, even like this, for center, symmetric, we would use mean. For spread, standard deviation. If it's not symmetric, it's skewed left, it's skewed right. We're going to use the median. And the 5-number summary for spread. So symmetric, we use the mean for center, standard deviation for spread. If it's skewed, we use the median for center, 5-number summary for spread. Okay. Now, which is better? Does anybody remember what I told you? Anybody from Zoom want to say what's better? No one remembers. No one wants.
Standard deviation.
Standard deviation is better for spread?
Depends on if it's skewed or not.
If it's skewed or not, that's right. So if it's skewed, if the mean is equal to the median, we use the mean for center, because the mean is the best measure of center, standard deviation is the best measure of spread. But if the mean's not equal to the median, we have to use the median for center. And someone always asks, well, why don't we just use the median? And the answer is because the mean is better, right? Right, cool. Okay, moving on. Okay, let's talk about percentile. Remember what the percentile is? That's the value such that P% of the observations fall at or above it. So if you're in the 99th percentile, then you are at or better than 99% of the people. Okay. One of my favorite graphs, the relative cumulative frequency graph, which we know better as ogive. Okay, so ogive, remember, it starts here and then goes up, goes up, goes up, goes up, goes up, whatever. Starts at 0, gets up to 100%. You can look at the steepness to tell how high each individual bar would be if it wasn't cumulative. Okay, time plots, we remember those? Yes, good, okay, time plot, axis time. Mean, median, measures of center. Let's talk about measures of center. Mean. When it's a sample mean, we abbreviate it X bar. The formula for the mean is on your formula sheet. It's just the sum of each individual x times 1 over n, or the sum of each individual x divided by the number of numbers there are, numbers in the data set. Median, it's just the number in the middle. If there's 2 of them, we take the mean of the medians. And mode, the one that appears the most. So if there's, you can have 1 mode, you can have 2 modes, or you can have no modes. So if it looks like this, the mode is 2. If it looks like this, the modes are 2 and 3. If it looks like this, there's no mode. Okay? All right, let's talk about spread. Range is just the maximum minus the minimum. That's an okay measure of spread, but not a great measure of spread. It doesn't really give you the whole picture. IQR, Q3 minus Q1, this gives you the middle 50%, how wide that is. If you want to do a box plot, this is min, Q1, median, Q3, maximum. This is what's called your 5-number summary. There's the width of the middle 50%. That's the IQR, okay? Outliers are 1.5 IQR above Q3.
Natalie Montoya to the main office. Natalie Montoya to the main office.
Did you get that, Miss Montoya? All right. 1.5 IQR above Q3, below Q1. So if there's some sort of outlier, we can do a modified box plot. Notice that would be a high outlier. Okay? Cool, cool. All right, moving on. Variance. Now, remember, when we find standard deviation is sort of an average distance to the mean. But if we took the distance of each individual x minus the mean, and we average those together, we're going to get 0. So what we want to do is we want to find the variance. So we're going to take each individual x minus the mean, square those distances, add them all up, and we divide by n minus 1. Now, we divide by n minus 1 because there are n minus 1 degrees of freedom. Okay? So the standard deviation S is just the square root of the variance. So the square root of this whole thing is S, standard deviation. All right, let's go to linear transformations. Linear transformations, changes x to x of nu. A plus bx. Okay, so we're going to add a constant, multiply a constant. Well, we multiply a constant, then add a constant because we know our order of operations. But that's about it. Okay, are we good? And that's all of chapter 1, and we're only like 10 minutes in. Life is good, we're getting there. All right, let's go to chapter 2. Density curves. Does anybody remember a density curve? Density curves always have two things about them. There is, they always have to be above the x-axis. They always have to have an area of 1 underneath it. So we could have a bell-shaped density curve. We could have a skewed right density curve, whatever we have. Now, on this one, this is the mean, median, and the mode. The mode over here is the high point. The median is the point where half the area is here, half the area is here. So the area to the left of the median is always 50%. The area to the right of the median is always 50%. The mean would be over here. This is the balance point if the curve were solid. Okay? So it would balance there. Just ask our physics teacher. All right, moving on. Now, when we used a sample, we used X bar.
Natalie Montoya. Natalie Montoya, to the main office, please.
That's going to be immortalized on YouTube forever. All right. When we did samples, it was X bar and S. When we do populations, density curves or theoretical population curves, we use mu and sigma. All right, let's talk about normal curves, okay? They're symmetric, they're single peaked, they look like this. Since it's symmetric, this is the mean, median, and the mode. It's symmetric, single peaked. We've got the mode here as well. Right here, at the inflection point, this is one standard deviation above the mean. At the inflection point over here, one standard deviation below the mean. So here would be 2, 3, 2, 3. Do we remember the 68, 95, 99, 7 rule? States 68% of the data is within one standard deviation of the mean, 95% is within 2 standard deviations of the mean, 99.7% is within 3 standard deviations of the mean. So if it's normal, we write it like this: normal with mean mu, standard deviation sigma. Okay. Z-score was always just x minus mu over sigma. This is the number of standard deviations a data point is above or below the mean. All right. Normal probability plots. If you look at your stat plot, this is the bottom right stat plot. If the normal probability plot is a straight line, then it's normal. If it's close to a straight line, it's approximately normal. It's a good way to just sort of look and say, oh, that's normal. Cool. All right. Chapter 3. Two new types of variables. Chapter 3 is where we did statistics with 2 variables. So we have the response variable and the explanatory variable. One is the dependent variable. This is the independent variable. This measures the results of a study. This explains the observed outcomes. This one's X, this one's Y. It's easy to remember. Explanatory has an X in it. Response does not have an X in it. Got it? Cool. All right. Now we put our 2 variable data in what's called a scatter plot. So it might look like this. Hey, look, a scatter plot. All right, X, Y, and we look at the overall pattern in the scatter plot. With describing a distribution, we did shape center spread. with the scatter plot, we're going to do form, direction, strength. Form is kind of like shape, but here this would be linear. The only form we're going to really need to worry about is it linear or is it non-linear? Direction, this one's positive. If it went like that, it would be negative. Strength, the correlation, how strong is it? Well, let's talk about that. Correlation, we abbreviate R, okay? R is that. On your formula sheet, don't have to memorize it. As you can tell, I still don't have it memorized. That's not true. Okay, so anyway, yeah, to find how strong it is, it's going to look like that. Now, some things about correlation that you might need to know. Doesn't matter which one's X, which one's Y, the correlation is going to be the same. Can we tell that changing X and Y isn't going to matter? Good. Variables have to be quantitative, clearly, because there's numbers involved. Okay, so you can't find the correlation between two categorical variables. There could still be an association, we'll get to that later, but for now, let's just make sure we know it has to be categorical variables. Units don't matter because it's standardized. If R is positive, then this is positive. That's important. R is between -1 and 1. If it's 1, it's strong and positive. -1, it's strong and negative. 0, there's no correlation anywhere in between. You can sort of figure out what that means based on that. It only works for lines, not curves, and it's not resistant. It's affected by outliers. All right, so once we get R, we can find the LSRL, the least squares regression line. So the regression line is the straight line that describes the relationship between X and Y. Basically, what we're doing is we are finding the line that's going to minimize the squares of the vertical distances from the points to the line. Okay, so the least squares regression line y hat equals a plus bx, where b. Do we have a question? No? Okay, cool. B is r times sy over sx, and every least squares regression line goes through the point x bar, y bar. So A equals y bar minus bx bar. Okay? On your calculator, stat, go over to calc. And the number 8 is linear regression, a plus bx. Do that, and you'll get it. All right. If you run linear regression, make sure that you have your diagnostics on, so it gives you both r and r squared. Okay. R squared is the coefficient of determination. Basically what R squared does is it gives you the percent of variation in Y explained by the least squares regression of Y on X. Okay? Everybody has that memorized? Do you guys over there in the Zoom chat have that memorized? R squared is the percent of variation in Y explained by the least squares regression of Y on X. All right, so let's talk about residuals. Residuals are y minus y hat. So this is the distance from the point to the line. Residuals can be positive if they're below the line, could be negative. Residual plot.
Hey, Rogan, you go ahead and take it. Just FYI.
Hey, thanks.
Appreciate it. Cool. That's all.
All right, so we want to go x in L1, y in L2, run the regression, store our equation in our y1, and then in L3 it will be L2 minus y1 at L1. That'll give us our residuals. Residual plot. The residual plot is L1, L3. If there's no pattern in the residual plot, then we know that the linear model is a good fit. Okay, let's talk about nonlinear regression. Nonlinear regression, we can do linear transformations, but if it's something nonlinear, nothing's going to straighten that out unless we do some sort of nonlinear transformation. So we talked about exponentials. In power laws, exponentials take the log of the y values. Power laws take log of x and y values. Okay? And, well, let's think about it. If it's an exponential, so that's log of y equals log a plus log of a is a constant, log of b is a constant, so we've just got the log of the y values equals a plus bx. If it's a power law, take the log of both sides. So the log of y equals the log of a plus p times the log of x. So we've got the log of our y values, log a is a constant, p is a constant, log x. So there you go. All right. Moving on. Cautions about correlation and regression. Remember, it only works for linear relationship. It doesn't work when it's nonlinear. When it's nonlinear, you've got to do the transformations. R isn't resistant. The least squares line's not resistant. We learned about extrapolation. Extrapolation is when you're outside the domain of X. So if I wanted to predict something, 20 years from now, well, something might have happened and who knows, right? Okay. Lurking variables, we remember these. So it's not among X or Y, but it may be causing something to happen. It may be why there's a relationship between X and Y is due to some lurking variable. Causation, X causes Y. Common response, X and Y are both caused by Z. Confounding, X might be causing Y, but it's probably also Z causing Y. So there's a difference there. All right, remember, most important takeaway was correlation does not imply causation. Okay, cool. Categorical data, we talked about two-way tables, right? Remember, marginal distribution, you add everything up, that's just your totals. So we looked at conditional distributions. If you're just looking at one category, that's the condition you're looking at. We talked about Simpson's paradox. Does everybody remember that? Simpson's paradox was when, hey look, this is better for both of these, but if I put them together, it switches. Okay, and yeah, let's move on to chapter 5. Look at that, half hour in, we're already through 4 chapters. Okay, chapter 5. Chapter 5 was our experiment chapter, designing treatments, designing experiments. We had experimental units. This is who or what we're studying. If they're human, they're called subjects. The treatment was the specific condition applied to the units. So, right, if we're testing something, testing a new drug to see if something helps, the drug is the treatment, the amount is the level. Okay. Placebo is no active ingredient. The placebo group is also called the control group. Okay, let's talk about the difference between the study and the experiment. Experiment is there's a treatment. Study is just, hey, we noticed something. If you want to show causation, you have to do an experiment. Okay? Population versus sample. Populations are really big, so it's hard to get everybody there. So we look at a small sample, and that will give us information about the population. Okay, so census is when we want information about the entire population. We don't do them very often, right? Okay, so let's talk about some sample methods. Voluntary response. Bad, right? Because it's choosing itself. You're only going to get people who really care. Now, if you're doing an experiment, you might need volunteers, but then you randomize them later. Convenient sampling. Bad, right? Convenient sampling is bad because, well, it's not going to give you a good look at the whole, right? If I were to ask everybody in this classroom, hey, you know, what any question about something, and I'm only getting the people that took AP Stats, I'm not getting the whole population. Okay? Bias, we know this, it's when it systematically favors certain outcomes. The best way to reduce bias is randomizing. So let's talk about simple random sample, or an SRS. This is every person, every individual, and every sample has an equal chance of being picked. Okay? We did a systematic random sample. Every individual, every person, every experimental unit has the same chance of being picked. but not every sample, okay? So this is if I said, well, let's pick a number at random, and I choose that number, just whatever row you're sitting in, or I choose a letter from the alphabet at random, and I say, okay, everybody whose last name ends with this, you get picked. Systematic. So everybody's got the same chance, but not every sample. Okay. Stratified random sample. Okay, in a stratified random sample, we separate into different groups before choosing and then choose. So if we want to make sure that all groups get represented, I can do a stratified random sample. Okay. Some cautions. Under coverage, non-response. So the difference here with under coverage, people are left out of the selection process. With non-response, they're selected, but they still don't get sorry, it keeps looking like somebody's there, but they're not. Okay. Non-response, they get selected, but they don't cooperate, they don't answer, whatever. Response bias. They lie or make mistakes. This could be due to the wording of the question. It could be due to what you're told before you get asked the question, all sorts of things. All right. So let's go back and talk about experiments. Experiments, we want to do control versus treatment. So we want to separate the groups into two different groups. One that gets the treatment, one that gets the control, the placebo. They should be roughly the same size. They should be, double-blinded means they don't know what they're getting, and the person giving them the treatment also doesn't know what they're getting. Okay, we've talked about a couple different experimental designs. Block design, match pairs. So a block design, this was, we separate the units into similarities, then randomize. With matched pairs, what we do is we give everybody both treatments, but randomize the order they get them in. Okay, we learned how to simulate experiments. So using a random number chart, we can assign, let's say, okay, we're going to assign this number for this number for this, and simulate it. Okay, chapter 6, probability. Probability, chance behavior is unpredictable in the short run, but in the long run it becomes very predictable. It should, in the long run, the theoretical probability and the empirical probability should be the same. Theoretical is what's supposed to happen, empirical is what did happen. Okay, so let's talk about some rules of probability. Probability of an event is always between 0 and 1. 0 meaning it can't happen, 1 meaning it's going to happen. Probability of S is 1. This is the sample size, or the sample space. Something's going to happen. Okay? Probability of a complement, the probability it doesn't happen is 1 minus the probability that it does. the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. The way that looks, it's this part, this whole circle A plus the whole circle B. You notice we counted the overlap twice, so we subtracted once. Okay? Probability of A and B is the probability of A times the probability of B given A. Now, if they're disjoint or mutually exclusive, this is equal to 0. So if they're disjoint, would look like that. There's no overlap, so this part's 0. If they're independent, then the probability of B given A is just the same as the probability of B. Okay? All right. We remember Bayes' theorem. We remember don't use it. Draw the probability trees out and do it that way. But make sure you remember that the probability of A given B is just the probability of A and B over the probability of B. Okay? And you can sort of figure it out from that. Just divide both sides. All right. Yeah.
So when you're checking for independence, if B given A is equal to B, that means that they're independent, right?
Yes.
Alright.
Yeah. Okay. So if the probability of B given A is just the probability of B, then they're independent. Okay? Like if we're flipping coins, the probability that I get heads the second time is still going to be a half, right? Even if I get heads the first time, it's not going to change the probability for the second time. So coin flips are independent. If I'm dealing cards, the probability my first card is an ace is 1 out of 13. My probability that the second card is an ace, now there's only 3 aces left, there's only 51 cards left, would be 3 out of 51. Those are dependent. Okay? We understand the difference?
Yeah.
Cool. Okay. All right, let's talk about random variables. Discrete random variables, continuous random variables. Discrete random variables are countable, continuous, or not countable. Okay? So if we have a probability distribution, whatever the probabilities all have to add up to 1. The probabilities all have to be at least, well, they can't be negative, okay? They have to be between 0 and 1 because they're probabilities, so they all add up to 1, okay? Expected value. Is just each individual x times its probability. The variance is going to be that. Sum of each individual x minus the mean squared times its probability. Standard deviation obviously is square root of the variance. Okay. If it's continuous, if it's discrete, we use this. If it's continuous, we have to use a density curve. The probability of something happening on when it's continuous is just the area under the density curve. All right. So let's talk about the law of large numbers. Okay, so if we're making observations at random from a population with mean mu and decide how accurately we want to estimate mu as the number of observations increases, x bar of the observed values approaches mu as accurately as you wanted and it stays there. Do we understand what that means at all? I said it really fast. Yes? Good? Okay. If you don't understand what that means, basically mu is always unknown, right? We don't know what the population mean is because the population's too big. But if we're looking at a sample mean, so let's say I wanted to find the average height of all the guys in the population, you know, let's just use the United States, there's lots of people there. So if I started picking people at random, hey, how tall are you? I'm 5'8". How tall are you? I'm 5'11". How tall are you? 6'1". How tall are you? 5'2". And I keep averaging them together. I keep getting closer and closer. It's going to keep getting closer and closer to whatever the unknown mean is. And it's not going to get very far away from it. So even at, you know, once I've picked 2,000 people, if I pick somebody who's 7 feet tall, which is way bigger than the mean, it's not going to move it that far, okay? And then it's just going to keep getting closer and closer to the mean. All right, law of large numbers, law of small numbers, there isn't one. In the short run, anything can happen, okay? All right, let's talk about rules for means. If I have two distributions, x and y, the mean of the two added together is just the mean of the first plus the mean of the second. Okay? If I have a linear transformation, the mean of the transformed data is just do the transformation on the original mean. Okay? So let's talk about rules for variances. With variances in a linear transformation, A doesn't matter, right? So if I'm adding something to everything, it shifts it, but it doesn't make it any further spread out. Okay, so the A doesn't matter. With B, I square it times the variance. So the rule for the standard deviation would just be the square root of B squared times sigma squared. Okay? The variance of x plus y, if they're independent, is that for x minus y, if they're independent, it's sigma squared x plus sigma squared y. If not independent, so this is if they're not independent, it's going to be this that's rho, that's the population correlation. So if I'm adding two together, 2 rho sigma x, sigma y, if I'm subtracting, it's going to be minus 2 rho sigma x, sigma y. Okay? All right, moving on. Chapter 8. The binomial distribution. Okay, 4 things. Each observation is in one of two categories, success or failure. Fixed number n of observations. Observations are independent. Probability, same for each, okay? So if we do that, we do a binomial distribution. The probability that x equals k is that. This is on your formula sheet. You don't have to worry about memorizing it, which is nice because it's a lot, okay? So this will tell you if I have 5 multiple choice questions, probability of each is 1 out of 5, okay? N would be 5, P would be 0.2. The probability that I get 3 of them right exactly would be 5 choose 3 times 0.2 to the third times 0.8 to the second. Make sense? Cool. Okay. If in P and in Q, Q is 1 minus P are both greater than or equal to 10, you can use a normal approximation for a binomial distribution. The mean is in P, the standard deviation is root NPQ. So let's talk about the geometric distribution. Everything's the same, except instead of a fixed number of observations, the variable of interest will be variable of interest is how long it takes to get your first success. So with this, it's that, okay? So that's not right. I did that wrong. That's better. 1 minus P to the x minus 1 times P. Okay, chapter 9. Does anybody remember chapter 9? All right, chapter 9 was where we learned the central limit theorem. So we had to do, we learned P hat, which was mean of P hat is P, standard deviation of P hat is root PQ over N. Okay. Central limit theorem, we remember that? Right, this had to do with the sampling distribution of x bar. So the mean of x bar is just the mean, the standard deviation of x bar is just sigma over root n. The central limit theorem said that if n is large, the distribution of the sample means is going to be approximately normal with mean, mu, standard deviation, sigma over root n. Okay, so as long as n is at least 30-ish or so, there we go. All right, inference. So we did confidence intervals. And hypothesis tests. Confidence intervals, we did step 1, step 2, step 3, step 4. All right, so on a confidence interval. Step 1, we want to know what the true mean or whatever in context of the problem. On a hypothesis test, we want to know if this claim is true, H naught, mu equals something, HA, mu is greater than, mu is less than, mu is not equal to something. Okay? Also, always in context of the problem. Step 2, conditions. What are our conditions? Okay, so, well, as a general rule, the conditions are always random, normal, sigma known, okay, or unknown. So if it's random, that's a condition for everything. Normal, okay, how is it normal? Well, if it's a z-test, as long as n is 30, we're good. If it's a t-test, n should be, well, the shape should be there. If it's not there, n has to be a little bit bigger, probably 40. If it's a proportion test, NP and Q both have to be greater than or equal to 10, okay? Same thing for hypothesis tests. So if it's, we decide what test are we doing? Well, if it's sigma unknown, we're going to do a t-test. If it's we're looking for a proportion, we're going to do a proportion z-test, right? NP and Q greater than or equal to 10. Sigma is based upon whether the population is at least 10 times the sample size. Okay, so step 2, we look at our conditions. What test are we doing? Step 3, do the test. Okay, now on your formula sheet it should tell you for a confidence interval it's always estimate or statistic plus or minus critical value times the standard deviation of the statistic. For a hypothesis test, it's always standardized test statistic is statistic minus parameter over standard deviation of statistic. So if it's z, it's x minus mu over sigma over root n. If it's t, it's x minus mu, and for mu it's mu naught, over s over root n. If it's 2 samples, use the 2 sample procedure. If it's 2 proportions, use the 2 proportion procedure. Okay? 4, interpret your results in the context of the problem. So if it's a confidence interval, well, if it's a confidence interval, we are 95 or 99 or whatever % confident that the true mean or the true proportion is within whatever we came up with in step 3. On a hypothesis test, we did this, we found the p-value. If the p-value is low, we reject H naught, okay? If the p-value is high, we fail to reject H naught. So if the p-value is low, we reject H naught in favor of HA. We have evidence to show that HA is true. If we fail to reject H naught, the p-value is high. Since our p-value is high, we fail to reject H naught. There's not enough evidence to show that HA is true, okay? Or there's not enough evidence to show H naught is not true. There's a lot of double negatives in here. Chapter 13, we did chi-square. This is just the sum of the observed minus expected squared over expected. Use the chi-square chart, find the p-value. That will not be on this year's AP exam. It'll probably be on next year's. You guys somehow got lucky, although I think I would have traded having to know chi-squared to still be in school. Chapter 14, linear regression inference. Find the slope. B plus or minus T star times the standard error of B. Over here, it's going to be just T equals B over SEB. And that's it. All right. That's it. Let's look at the Zoom. Does anybody in Zoom have any questions? Do you guys have any questions? No? All right. I'm going to call this good. That's 61 minutes and 5 seconds. Half an hour to spare. Not bad. Thanks to you guys. I'll come talk to you guys in a minute. Yeah, thanks for listening.